Hello, everyone. We apologize for the delay, but we want to welcome you all to this free webinar hosted by WePast. My name is Christina Ruiz, and I will be your moderator today. Throughout the webinar, we will stop the presentation to review. There will be multiple choice poll questions, which you will be able to answer in the sidebar. Please go ahead and answer these questions as they come up. This and other recorded webinars will be available to WePast subscribers. You can register through wepast.com to become a subscriber. Today's topic, Monte Carlo Methods in Radiation Therapy, presented by Michael Fix, PhD, the Deputy Head of the Division of Medical Radiation Physics at the University Hospital Bern in Switzerland. Thank you for joining us, Michael.
Welcome to this presentation about Monte Carlo methods in radiation therapy. When talking of Monte Carlo, some of you might think of the city at the Mediterranean Sea, the Formula One race, or the ATP tennis event currently running in Monte Carlo. However, the Monte Carlo method is linked to the casino in Monte Carlo, which is shown here. Similar to the gambling in the casino, the Monte Carlo method is using gambling in order to simulate particle trajectories forming the radiation transport through media. Although there is no unique definition of Monte Carlo methods in terms of its application in medical physics, I found the following expression to be the most appropriate. It is a numerical method to solve equations or to calculate integrals based on random number sampling. Even though this is still a very general definition of Monte Carlo, it states that the transport equations are numerically solved using random number generators. But before going into the details, I would like to show the outline of this presentation. After a short introduction covering some history and the basic definition of terms used in Monte Carlo, a few features about random number generators will be presented. Along with an example of a simple radiation transport, the components necessary for a Monte Carlo system will be introduced. Then the uncertainty as well as the efficiency of Monte Carlo simulations are discussed. Finally, some comparisons with other dose calculation algorithms will follow before the summary will finish this presentation. The term Monte Carlo coined in 1947, but the use of stochastic sampling methods is much older. The first proposition of such a method was to determine the solution to the needle problem of Buffon. Buffon looked at bars with a distance d and was asking himself what is the probability that dropping needles with a length L smaller or equal the distance of the bars to cross the bar. So one could drop many needles and count the frequency of those crossing the bar. It turns out that the probability is 2 times L over pi times d. Thus pi can be estimated by counting the needles crossing the bar, determine the mean value, and apply this formula. Now these days we can use computer programs to drop the needles randomly on the bars and estimate the value of pi. Using 10 needles demonstrate that pi is rather roughly estimated. In order to achieve a better statistical uncertainty of pi, more needles have to be used. This is a general feature of Monte Carlo in that many repetitions of the event are necessary to receive a reliable estimation of the quantity considered. So using, for example, 2000 needles, the following figure is achieved. One can see that the number of needle drops is increasing the better the estimation of pi gets. This demonstration leads to two important terms in Monte Carlo: precision and accuracy. First, we deal with precision. It can be seen that the range of estimated values decreases with increases number of needle drops. That means the underlying statistical uncertainty or precision is decreasing. The lower the statistical uncertainty is, the less uncertain the estimation of the mean value is. Thus, quantities determined with Monte Carlo are always associated with an intrinsic statistical uncertainty. Overall, an infinite number of repetitions have to be simulated for zero uncertainty. On the other hand, the mean value itself converges to a certain value, which is normally the true value. In this case, the true value is pi. How close the simulated value reaches the true value in convergence is termed accuracy. Thus, accuracy is not the same as precision. And any Monte Carlo simulation of a quantity is a noisy representation of its true value. And with each mean quantity determined with Monte Carlo, should always its statistical uncertainty be stated. Otherwise, it remains unclear on how reliable the mean value really is. However, it could also look different. In this case here, the statistical uncertainty still looks the same and decreases with increasing needle drops, but the mean value does not converge to the true value anymore. One reason why this happens is using an inappropriate random number generator. Thus, what are the features of random number generators used in Monte Carlo simulations? First of all, computer programs are used for this purpose. So as the output of any computer program is per definition predictable, not true but rather pseudo-random numbers are produced. The features of such pseudo-random number generators are the following. They should be uncorrelated. They should be uniformly distributed in multiple dimensions, typically sampled in the interval between 0 and 1. They should provide a long sequence. They should provide a reproducible sequence. And it's a great feature if they produce the same sequence on different machines, make them easily portable. Although not true random numbers, the pseudo-random numbers are just called random numbers as well, so don't get confused. Two examples of random number generators are provided here. The first, RANMAR from CERNLib, with a very long sequence of 2 to the power of 144. RANMAR is used in EGS4, EGS NRC, and XVMC. Another example is RANDOX, which is a generator with different luxury levels between 0 and 4, with increased quality and computation time for increased luxury level. RANMAR corresponds to RANLux with a luxury level of 1 to 2. Other good sources are Root, which is a framework within CERN libraries, and the CERN program library itself. One difficulty with random number generators is to test their quality. There are several tests available and mostly checks are used where the true result is known, like the simulation of pi shown in the beginning. This brings me to the quiz question series 1. Which statement is false? Random number generators used in Monte Carlo simulations need a long sequence. Testing the quality of random number generators is complex. Random number generators provide reproducible sequences. Typically, not true random numbers, but rather pseudo-random numbers are used in Monte Carlo simulations. Platform-independent random number generators are of advantage in Monte Carlo simulations. So I give you 5 seconds to think about the right answer. And the right answer is random number generators provide irreproducible sequences. They still can be reproducible if they start with the same initial conditions. The next part determines the components needed for Monte Carlo code system. The first one we already know, which is the random number generator. The other components are elaborated using an example of a very simple radiation transport. So we start with photons incident on a cubic geometry with a homogeneous material as shown here. We consider just 2 photon interaction processes. One is absorption with a total cross-section of mu absorption, and the second an inelastic interaction with total cross-section mu elastic and uniform direction distribution for the scatter angle, as shown here. The photon should be terminated when leaving the geometry, like here. In order to illustrate the simple transport, particle tracks have to be determined using the following procedure. First, sample distance to the next interaction from the Beer-Lambert law, E up to the minus mu x, where mu is the sum of the two interaction attenuation coefficients. Transport the particle to the interaction point considering geometry constraints. It's the next point. Third, we sample the interaction type, either the absorption with a probability of mu absorption divided by the total mu, or the probability for elastic scattering. Next, we simulate the sampled interaction, so either the termination for photons undergoing absorption, or sampling the scattering angle for elastic scattering. Finally, we repeat step 1 to 4 until the photon is leaving the geometry, or is absorbed, of course. This procedure is implemented in Python and is presented in the following slides. You might use this example and gamble by yourself. First, some initialization have to be performed. This starts with a number of histories with a relative absorption attenuation coefficient and elastic scattering attenuation coefficient. We need to define the geometry and the source of the starting photons. Second, the distance to the next interaction is sampled using the Beer-Lambert law with a previously defined attenuation coefficient. In this case, the random number generator samples a random number uniformly between 0 and 1, and then the inverse function determines the distance to the next interaction. This distance is applied to the particle track. The next step is to check if the sample distance already exceeds the geometry. For this purpose, one needs to check all 6 planes of the simple geometry. This could be rather difficult for more complex geometries. Given the particle is still within the geometry, the interaction is sampled. Again, we use an interval between 0 and 1 and divide this interval in 2 sections. One is proportional to the elastic scattering interaction mu elastic divided by the total attenuation coefficient. The other part will then be proportional to the probability to undergo absorption. Again, a uniformly distributed random number generator samples a number, and depending in which section the number is, the interaction is used. This can be realized in a single command line in Python. If the expression is true, an elastic interaction is sampled, otherwise the particle is absorbed. In case of the absorption, the photon track stops, while in the case of an elastic interaction, the isotropic scattering angle is determined using this sampling routine. Finally, we need to provide the main framework to the simulation tool. First, looping through the number of histories. Then the history here loops through the individual steps until the track is within the geometry. The resulting tracks can then be plotted showing particles without any interaction, going through with straight lines, which are directly absorbed, and those undergoing several elastic interactions. So now we can name the components of the Monte Carlo code system. Besides the random number generator, there is the sampling procedures, we need to have the physics input, namely the cross sections. We need to define the source, the geometry, and the material, as well as we have to have a bookkeeping and an output feature in place. This leads me to the quiz question 2. Which component does not belong to a Monte Carlo system? Physics interaction data and transport parameter, energy deposition kernel, description of components to be simulated, seeds for the random number generator, a counting system. Give you another 5 seconds. So the right answer is the energy deposition kernel. They are linked to the convolution superposition algorithms. As already mentioned, the statistical uncertainty is of great importance for the Monte Carlo simulations. Often it remains unclear on how the stated number of percentage uncertainty for a dose distribution is determined and what its meaning is. We first consider the situation for dose calculation of electron beams in a water phantom with scoring voxel and an impining electron beam. If dose calculation is repeated, each time a different dose distribution is calculated with Monte Carlo, since the random number generator is started with different starting conditions. So these dose distributions differ in the statistical uncertainty. This uncertainty depends on several settings, such as number of incident particles, voxel size, field size, beam energy, and so on. These uncertainty are also different from voxel to voxel, as Monte Carlo determines the mean value with a certain precision in each voxel. For dose values close to the maximum dose, the relative uncertainty is smallest and the absolute uncertainty is largest. For low dose values, it is the other way round. Now we consider an average of n electrons impining on the phantom. Each electron is an electron in an electron beam, has about the same energy and thus about the same energy deposition in a traversing voxel, leading to about the same dose contribution per electron. This means we have a Poisson distribution with parameter lambda, and the mean and variance is given by the mean number of electrons. The standard deviation is the square root of n, and the relative standard deviation is 1 over the square root of n. That means the precision of the electron dose distribution per voxel decreases with the square root of the electron fluence hitting the scoring voxel. For example, voxel with a 10 by 10 square millimeter voxel surface result in a relative uncertainty of 1% for an electron fluence of 10,000 electrons per square centimeter. Reducing the voxel dimension by a factor of 4, a fluence of 160,000 electrons per square centimeter is needed to achieve, again, an uncertainty of 1%. So for the specific conditions of electron beams, one can determine the uncertainty based on the fluence. In general, this is not possible due to the fact that photons are indirect ionizing. The general approach is the following. We simulate n random events I. We score the quantity f of interest for these events fi. We estimate the mean and the standard deviation. The mean value and the standard deviation are determined as usual, and typically the standard deviation of the mean is considered for the statistical uncertainty. This value can be expressed with the mean of the squared quantity f and the square of the mean value of f. With the central limit theorem, it follows that the mean value of f converges to the true mean and the same for the standard deviation leading to a normal distribution. With this approach, we can also consider the statistical uncertainty for photon dose calculations with Monte Carlo. Again, we have the water phantom with impining photons leading to a dose distribution. Now the simulation of n random events correspond with the simulation of n independent photon histories. The scoring quantity is in this case the energy deposition, and the estimation of the mean and standard deviation follows the previous formula. As we do not have a Poisson distribution in this case, we cannot directly link the fluence to the standard deviation. However, we can determine the ratio of uncertainties and connect this ratio with the fluencies. Thus, given a first simulation with a fluence n1 and standard deviation s1, one can estimate the fluence n2 needed to achieve a standard deviation s2. Typically, the standard deviation is provided per voxel, but rather an average of those is used. Thereby, such an average is taken over all voxel with dose greater than x% of the dose maximum. Normally, x is 50, but also other values can be used. Now, several different approaches are possible and in use. One can take the average of relative statistical uncertainties in percent. We can use the average of absolute statistical uncertainties and express this relative to the Dmax in percent. Or we can do both of these methods, but taking the average in quadrature. One example comparing these approaches is shown here, using an x value of 50 and 90. The numbers slightly different for the different approaches and are lower when the absolute standard deviation relative to the maximum dose is used. The most conservative method averages the relative standard deviations in quadrature. Another example of such an evaluation shows a different result. While for a dose threshold of 50%, 6% uncertainty is documented, the value is above 99% for a threshold of 90%. This looks strange. So what happened? In this simulation, there is a high dose outlier, so only 2 scoring voxels are considered for the average of the uncertainty. This also demonstrates that in Monte Carlo simulation, extreme values like maximum or minimum dose, etc., are crucial to use due to their sensitivity to large statistical uncertainty. This brings me to the quiz question number 3. Which statement is true? The statistical uncertainty determines the accuracy of the Monte Carlo simulation result. The accuracy of Monte Carlo simulations increases with increasing number of histories used. The statistical uncertainty is determined for dose calculations but not for fluence simulations. For Monte Carlo simulations, the statistical uncertainty is less relevant than the accuracy. The statistical uncertainty of dose distributions for electron beams can be estimated based on the impining electron fluence. Give you another 5 seconds. So the true answer is the statistical uncertainty of dose distributions for electron beams can be estimated based on the impining electron fluence. Now, what are the potential benefits of Monte Carlo in radiation therapy? First of all, it's named its accuracy. The accuracy can be of advantage for small radiation fields, regions with large dose gradients and radiation disequilibrium, as well as in heterogeneous conditions. Furthermore, it has its value in benchmarking for certain situations and algorithms. And another important feature is that it provides information which is not available with measurements. For example, the physical characterization of scatter radiation or energy distributions. Of course, there are also some downsides of Monte Carlo, one of which is the speed. While we have seen in the previous presentation that correction-based dose calculation algorithms are extremely fast but limited in accuracy, the convolution superposition algorithm provide improved accuracy on cost of calculation speed. This trend is continued for Monte Carlo methods. Another aspect is the statistical uncertainty, which is present in the dose distribution. Its effect is on isodose contours is presented here for 10% statistical uncertainty, for 2% and for 0.5%. A low uncertainty is necessary for a smooth presentation, and thus a long calculation time is needed. Since dose volume histograms integrate dose value, the effect of the statistical uncertainty is less prominent as shown in this example. The description of calculation time and achieved statistical uncertainty is combined in the efficiency of a Monte Carlo simulation as stated in this formula. Thereby, the calculation time is determined by the calculation time per step multiplied by the number of steps per history and the number of history itself. In general, the true variance here cannot be calculated as the true mean value is unknown. However, the estimated variance S can be used instead. Now, a lot of effort has been spent to develop variance reduction methods of Monte Carlo simulation, such as particle splitting. It is worth mentioning, though, that the efficiency is always stated for a certain hardware, and thus replacing the hardware is not considered as a variance reduction method. As the efficiency is not only depending on the variance but also on the calculation time, the aim of variance reduction method is rather to improve the efficiency of the Monte Carlo algorithm. Basically, there are two different types of variance reduction methods available. The first one is the efficiency improvements through the use of approximations, which are the approximative variance reduction methods, and those techniques that does not alter the physics in any way when it increased efficiency. That means it does not influence the expected result of any infinitely long Monte Carlo simulations. Those are called real variance reduction methods. Simple examples are the energy cutoff for particle transport. That means electrons or photons with an energy below this energy cut are discharged. Another example is the already mentioned particle splitting, where not just one secondary particle is generated, but many of them. This also means that no Monte Carlo algorithm is without approximation, since all codes are using cutoffs for the particle transport. And we are already at the quiz question 4. Which of the following statement is false? The efficiency of Monte Carlo calculated dose values is higher for photon beams compared to electron beams. The statistical uncertainty of the Monte Carlo calculated dose can be recognized during plan evaluation. Monte Carlo simulation can provide information which is not directly accessible with measurements. The efficiency of the Monte Carlo dose calculations can be improved by variance reduction methods. Monte Carlo algorithms for dose calculations are accurate but slow. Another 5 seconds to think about the right answer. The answer is the efficiency of Monte Carlo calculated dose values is higher for photon beams compared to electron beams. Think of that photons are indirect ionizing particles, so the electrons has to be produced first. The last part of the presentation deals with the comparison of those calculation algorithms. First of all, there are some general considerations about such comparisons. There exist different purposes of such comparisons, such as to determine the accuracy of the dose calculation algorithms, or to determine the limits of the dose calculation algorithms, or the practicability in clinical routine. Depending on the purpose used, the design of the comparison study looks different. But also the conclusions in such comparisons might be different. It could be the avoidance of using the dose calculation algorithms in unsuitable situations, or the change to another algorithm. However, this might be difficult since the clinical experience is based on the old algorithm. Also, different strategies are used for these comparisons. one could think of keeping the same parameters such as voxel size, DVH calculation, blind comparisons using same monitor units, or using the same normalization. One can also analyze different endpoints. One can perform the comparison on phantoms or on patient datasets depending on the purpose. Typically, with all these comparisons, no quantification on clinical significance is made. After these rather general comments on those comparison studies, clinical examples will be shown. The first example is a comparison of pencil beam, shown on the right, and Monte Carlo, shown on the left, calculated dose distributions for a lung case using the same number of monitor units. The dose degradation when switching from pencil beam to Monte Carlo is clearly seen in the isodose levels, but also in the DVH, especially for the PDV. Thus, switching to Monte Carlo for this case is difficult, as the prescription would have to be adjusted as well. The second example is a head and neck case illustrates a less dramatic change between pencil beam on the left and Monte Carlo on the right. The corresponding DVHs also include the AAA calculations. The coverage decreased from pencil beam to AAA to Monte Carlo using the same monitor units. Now I will go quickly through 3 published papers, each dealing with dose comparisons for different particle types. The first is comparing electron beam using VMC++ Monte Carlo calculations, Gaussian pencil beam, and measurements. In general, pencil beam algorithms are less suitable for electrons due to the in-air scatter. That means ray tracing is difficult and the inverse square law is not working that well. Thus, nowadays almost all commercial treatment planning systems offer a Monte Carlo-based electron dose calculation algorithm. Here, for a small air inhomogeneity, the dose profile in 3 depths for a 9 MeV electron show that the pencil beam almost ignores the inhomogeneity, while Monte Carlo follows the shape of the measurements. Similar observations can be made for small bone inhomogeneity, again for 9 MeV electron beam. In case of a trachea spine phantom, the small gaps between the spine it's not seen by the pencil beam algorithm, while Monte Carlo is able to predict the dose increase at these locations. On the left, the situation for 9 MeV electron beam, and on the right for 20 MeV beam is shown. The next publication compares many different photon dose calculation algorithms from different vendors and EGS NRC Monte Carlo. Dose distributions are calculated in a lung phantom within water, using 2 different lung densities, 2 beam energies 6 and 15 MV, and 2 field sizes, a square and an elongated field. While there is still an agreement for most algorithms when using a 6 MV large field, this changed for small fields and higher energy, and getting worse for 15 MV and low lung density. While type A algorithms fail, type B algorithms are able to more accurately predict the Monte Carlo dose calculation values. This separation is also visible in the corresponding dose profiles. A paper in 2011 from the same group provided some updates with respect to AAA, Acuros, and Monte Carlo, showing roughly the same shape for Monte Carlo and Acuros. Finally, for protons, a comparison using pencil beam and VMC Pro Monte Carlo is shown for 2 phantom situations. The first situation included a slab phantom of soft tissue, bone, lung, soft tissue configuration, and a proton pencil beam with 100, 150, and 200 MeV. Depth dose curves on the left, integrated depth dose curves in the middle, and dose profiles for 100 MeV on the right are shown. In this case, the pencil beam algorithm is able to accurately predict the Monte Carlo dose distribution. In the case where the boundary of the inhomogeneities is along the pencil beam, which is the most challenging situation you can think of, one would expect two Bragg peaks as seen with Monte Carlo. However, the pencil beam does not. This can be improved by using subspots within the proton pencil beam. However, there are still differences, which can be somewhat further reduced by using an adaptive procedure where the number of subspots depends on the voxel size and the initial spot size of the beam. Still, the last quiz question is left. Which of the following statement is true? Given proper QA, switching dose calculation algorithms in clinical routine is straightforward. Comparing dose distributions need the same monitor units and the same normalization. Most treatment planning systems provide a Monte Carlo dose calculation algorithm for electron beams. Monte Carlo dose calculation algorithms show only minor differences to other algorithms. Clinical medical physicists need not much knowledge about the different dose calculation algorithms. The right answer is that the most treatment planning systems provide a Monte Carlo dose calculation algorithm for electron beams. Now I conclude with the summary. Monte Carlo techniques is a flexible as well as an accurate tool in radiotherapy. Monte Carlo simulations are always associated with a statistical uncertainty which needs to be specified. The MC simulations of a simple radiation transport show all necessary elements for general and much more difficult problems. Broad range of applications in radiotherapy, especially dose calculation, is possible. The accuracy depends on the accuracy of the input data, the commissioning of all parts. Variance reduction methods allow efficiently simulate radiation transport. There is some caveat. There is no exact Monte Carlo code. All use certain physical approximations within a given range of applicability. Therefore, all codes need fine-tuning of their transport parameters according to the problem to be solved. And all in all, Monte Carlo simulations are most accurate if used appropriately to problems in medical physics. Generally, CPU time is no longer an obstacle for clinical implementation of Monte Carlo techniques. And for those who would like to know more about Monte Carlo in radiation therapy, I recommend this book, edited by Secco and Verhaken. And with this, I thank you for your attention.